Okay, this is another simple proof involving relations and sets. We're going to work with the relations R and S, and both of these relations are from A to B, so we know what that means. We know that that means that R is a subset of the Cartesian product with A and B, and S is also a subset of the Cartesian product A and B. And what we are going to do in this problem is we are going to show that the set R unioned with S inverse is equal to R inverse union S inverse. So usually when we deal with sets, we do this, and we want to show equality, we do it in two steps. We show that the left side is a subset of the right side, and the right side is a subset of the left side. So by showing that each is a subset of the other, we establish that these sets are actually identical to each other. So let's go ahead and do that. Let's start off with an arbitrary element in the set inverse of R union S. And then we're going to show that this is actually in R inverse union S inverse. All right, well, if A comma B is an element of the inverse of R union S, by the definition of the inverse, this means that B comma A has to be in R union S. So I basically applied the inverse to both sides. So if AB is an element of the inverse set, that means BA has to be an element of the non-inverse set. So I flipped that coordinate. What does it mean for B comma A to be an element of R union S? Well, that means that either BA is in R or BA is in S. That's just the definition of a union of sets, right? So that's pretty easy to see. Well, if BA is an element of R, that's equivalent to AB being an element of R inverse. Okay? So instead of writing the statement B comma A in R or B comma A in S, it's equivalent to A comma B in R inverse or A comma B in S inverse. And then finally, this is just the definition of union again, right? Anytime we have ORs, instead of A comma B in R inverse or A comma B in S inverse, that's equivalent to A comma B being in R inverse union S inverse, just by the definition of the union. So we've established that A comma B is in R inverse union S inverse. So we've shown that R union S quantity inverse is a subset of R inverse union S inverse. So that's the first half of the proof. For the second half of the proof, we do the exact same steps, just backwards. So let's start with A comma B in the right-hand set. And we can basically just walk through these steps in the exact reverse order we just did them. If AB is in R inverse union S inverse, by the definition of the union, that means A comma B is in R inverse or A comma B is in S inverse. That's just the definition of the union. If A comma B is in R inverse, that's equivalent to B comma A being in R. Similarly, if A comma B is in S inverse, that's equivalent to B comma A being in S. So this is our new logical statement. By the definition of the union, this means that B comma A is in R union S, because that's just the definition of union. And then finally, I'll apply the inverse to both sides to get A comma B is in the inverse of R union S. So we've started with an arbitrary element in R inverse union S inverse, and we've shown that that element is in the quantity R union S inversed. So we've shown that this is a subset this way. So in part 1, we showed that the left-hand side was a subset of the right-hand side. In part 2, we showed that the right-hand side was a subset of the left-hand side. So this establishes that these two sets are indeed equal to each other.